Jetzt sind wir schon wieder am falschen Bild. So, hello, welcome. Today we are going to start the exercise in assembly and packaging technology. And also, not all have joined yet. I will start. Also, you will have the recording of this exercise, so you can look up what I told you and how I instructed you anytime. Nevertheless, some remarks. It is of utmost importance that before we go into the exercise, you have prepared yourself well with the lecture which you could download and which you could attend electronically. So it makes not much sense to do exercises without understanding or without having previous information. Okay, today I would like to start and the question is, why do we have assembly and packaging? And that would be the first exercise question that I would like to treat. And here my question is, what are the four functions of assembly and packaging technology? So the question would be, yes, what is it, what assembly and packaging is for? So now I have a small problem because I do not know if you can ask me questions or how we can get this managed. Wo mache ich das? So, sorry.
Sie können sich selber entmuten. Die Studenten können sich selber entmuten.
Okay. So, the information I got, you can unmute yourself, so that is important. You stay muted normally in order to avoid any acoustic feedback loop. So if you want to say something, you unmute, and in that case, then maybe it would be good if you just say your name. And so we still have to exercise this and to get used to using this system. So is anybody who would like to make a remark now? Ja, muss ich jetzt die Leute, wenn hier Stummschaltung aufsteht? Okay. Could someone of the audience make a remark so I know I hear you? Okay, Mr. Alvarado, nice to hear from you. Also, Mr. Scharla, you have a remark? Okay, so. Then let's proceed. Why do we have assembly and packaging? And the most important thing is, first of all, we want to have a package that can be handled. So handling, processing is something which is very important. For instance, you make a pick and place operation and place this package on a printed wiring board, for instance. What is another important function? That would be, for instance, electrical interconnection. It is important that a package protects the chip which is inside it. So against environment, against mechanical impact, and so on. What else is necessary? Normally, a chip dissipates heat, and so it's also important to get rid of that heat and to conduct the heat into the environment. And to that purpose, we must have a heat management. Or as we say, thermal management. Another aspect is that there can be other interactions. For instance, we can transfer fluid or pressure and so on. So for instance, media interfacing. So I don't talk about social media or multimedia, but like liquid, gas or so. Okay, in that way, all of these aspects have to be optimized, and that's one of the parts of this lecture and exercise, to show how to make the optimum package or the best suited package for a certain purpose. And on the other hand, also it is the question which properties of electronic hardware are affected by assembly and packaging. And which properties do we have? It's typically when you ask someone from industry, what will industry people say? What is the most important property of a product? It is costs. For engineers, it shouldn't be costs in the first place. That's more for the people from the maybe sales department. On the other hand, what is very much important is reliability. Reliability, what kind of property is it? It is a probability that it will not fail. And so low failure rate means high reliability. And as there are many portions of the package that can fail, it can the packaging will contribute for more than 50% to reliability. So in both cases, it's more than 50%, more than 50%. Then we have other properties like electrical properties. So, we mostly have some parasitic properties, and these consist of resistance, they consist of capacitance and inductance. And you could say, okay, By resistance, you have losses. You will generate heat, and the efficiency will be degraded. By capacitance, signals can be slowed down, but capacitance can also contribute to losses. And inductance also slows down signals, or you have some cross-coupling. And so electrical properties are significantly affected. Another aspect is, for instance, size and weight. So if you look at how small a chip is nowadays, it's only in the cubic millimeters range, and on the other hand, the size of the package rather goes into the cubic centimeter range. So that means it's very important to make also the assembly and packaging as small as possible. Okay, that was the questions which highlight why we do assembly and packaging and why we have to deal with this. Also, I would like to mention again that there are three aspects of assembly and packaging. The first aspect is the principle, how the principle of a package element is. The second is the material. So, which materials do we use to build this? And the third is the fabrication process, how it is produced. And all three aspects are important in order to understand assembly and packaging. So, certain materials have to be processed in a certain way, and also the properties which we can achieve depend very much on these materials. Okay, and now the question is, describe 4 principal elements of a molded plastic package and its materials. And what is a molded plastic package? Again, here we have the question for the fabrication process, and first part of this process is the complete sequence to get from the elements to this package, and the second is, of course, the molding process itself. And to make it short, we can have a look what the elements are. The best is always to make a sketch in order to see where these for instance, that could be a lead frame. Okay, and this lead frame, typically it's for instance, it's a copper alloy. And on this lead frame, the chip has to be mounted. To that purpose, we frequently use an adhesive. For instance, that would be epoxy silver adhesive. I hate this. Then we need a chip. So the chip, after it has been glued on top here, of course we have on the chip surface metallization. Maybe we don't go into the details here, but for that purpose we also need some wire bond. Okay, so what's the material here? We can say it's typically gold wire. Diameter typically is 25 micrometers. And so we have 1, 2, 3, 4 elements. The chip doesn't count, so it's 3, and now we need the package body. Okay, and that's it. Of course, it's all filled up with molding compound. And that's our package, and so we have the molding compound. And it's also epoxy material plus, typically it's filled with silicon oxide. Okay, in that way we have produced a package. There is one question I have. Why are these side walls here of our package, why are they not rectangular, but they have a certain angle? Do you have an idea why we have this shape here? So yes, so it's to improve the release from the mold, and so maybe it's an angle of, I don't know, 5 degrees or so from the rectangular angle, and in that way it is easier to take it out, because in the molding process it's still warm, and so the material is not too hard, and it could also stick a little. And if you want to release 1,000 such elements simultaneously, you would have a real problem if only one of these would stick in the form. Okay. So also that's one of my ideas I have. One should not just learn by heart facts, but you should always try to understand why is it so? Why do we have this special step? Why this modification and so on? So it's better than just learning facts alone. Okay, so we have already seen the lead frame, and the question is, what kind of material should a lead frame be be. And of course, there are quite some requirements which are important. And one of the requirements is that it is a metal, so it can be formed by some deformation, by some stamping and bending and so on. So it must be soft enough, and it must be deformable or ductile, we say, enough to form such leads, for instance. On the other hand, in assembly and packaging, after we have accomplished the package, there are many interactions, and so what are the relevant properties? One of the properties is the CTE. That's the coefficient of thermal expansion. Typically, we take an alpha as the sign, and the CTE is measured in ppm per Kelvin, or 10 to the power of -6 per Kelvin. 1 Kelvin is same like 1 degree centigrade. The difference is Kelvin is the absolute temperature, and if we give temperature differences, we always give them in Kelvin, not in degree centigrade. Okay, of course, the offset between both is 273 Kelvin. Okay, what is the second property? That's the heat conductivity. So the sign is a lambda, and it is given in watt per meter Kelvin. So that's not so easy to understand. We will see it later on. And here we have now the question for the materials which we use. The most important lead frame materials are copper alloys. One very important alloy is, for instance, copper, iron 2, and having a little phosphorus for some electrical reasons. So that's the copper alloy. And the second is so-called alloy 42. That's an alloy which is iron 58, nickel 42. It's you could say it's some kind of stainless steel with a very high nickel content. Now, what is the advantage of copper alloys? The advantage of copper alloys is that it preserves the high thermal conductivity of pure copper. So typically it's roughly 260 watt per meter Kelvin. That's a very high value. Pure copper has roughly 400. Alloying always degrades conductivity. That's both in thermal conductivity and in electrical conductivity. The CTE here is very similar to the CTE of pure copper. Here you could say it is roughly 16 ppm per Kelvin. Please note the CTE is mostly determined by the crystal structure, and the crystal structure is not affected by this 2% of iron. Okay, so it's 16 ppm per Kelvin, or some also say 16 micrometer per meter and Kelvin. That means if it's a meter bar and you increase temperature by 1 degree, it will expand for 16 micrometer. Why do we have this 16? That is well matched to what? What should have a very similar CTE like that copper CTE? Do you have an idea? Sorry, can you repeat it, please?
I think the printed board.
Yes, that is correct. The printed wiring board, some say also printed circuit board, and in that way you do not have so much stress on the solder joint. On the other hand, alloy 42 is not used so much anymore, but in cases where we want to have a very good match with the silicon, we have alloy 42. It is an alloy which is also very similar to the Invar alloy, and Invar doesn't expand at all at low temperatures or contract. But here we have roughly 4.5 to 5. Also in literature we find different values, and so it's roughly 4.5 as a CTE, and so it's very similar to the silicon. Unfortunately, the heat conductivity is low, so it's poor. It's only roughly 25 watt per meter Kelvin. Okay, so that are the lead frame materials, and we have also seen what other properties are. Both materials conduct electrical current very well, but that conductivity is so good, it is in fact never really a problem when you regard lead frames. Okay, now let's have a look at the molding compound. In fact, when we look back, and if we look into the material, let's say from here, so we see very many small dots. So we have seen it in the images from the lecture notes. These small dots are making up, let's say, most part of our molding compound, and that is silicon oxide. Also some silicon oxide with a somewhat different composition, and here the mass content is somewhere, so in percent, it's somewhere in the 80% region. Maybe what of course is important is the epoxy resin plus hardener. So for instance, if we would say 15% roughly plus maybe 2%. So the content of epoxy, which keeps it all together, it sticks it together, is much lower than the silicon oxide. The silicon oxide brings down the CTE of that material. What else do we have? We have carbon black. it's somewhere in the percent region. So it's important not to have light come into the package because many semiconductors are light sensitive. There are other constituents. For instance, we have some kind of waxes. So it's for mold release. So it's also in the percent region. And we have adhesion promoters. I don't know, it's in the few percent range. It cannot be too much because otherwise the material would start to conduct, and that is, it must be a very good insulator, so we can only have a very small amount. In fact, the precise compositions are typically not given by the manufacturers of such molding compounds. It's typically their secret. I have a colleague here in Freiburg, Professor Mühlhaupt. When he was younger, he was working in development of molding compounds, and he told me, we mixed in 20 ingredients into a molding compound, but only of 10 we understood what the effect was. And also in polymers, often some substances are mixed in just to make it harder for the competitors to analyze what is in. So it's rough values to give you a guess. So now let's have the adhesion promoters finally. So it's also in the percent region, so it's silanes or something. Of course, that goes to the lead frame. And that is from the steel mold. Okay. Let's go ahead. Now, the next exercise says, name 2 modern package types for components with high I/O numbers. Describe these with a sketch. The package I was showing already is not a modern type. So it's a SMD type, surface-mounted device, but these were initially introduced around 1985 or so, 35 years ago. And these SMD with the lead frame were mainly based on previous through-hole packages. So the main difference was that the leads were bent to the outside, so you could solder these on the printed wiring board. But now let's have a look at modern package types for components with high I/O numbers. High I/O numbers, I would say possibly more than 64 or so, and going up to, let's say, 640 or similar order of magnitude. And what's the main working horse of packaging for large I/O number? That's the so-called ball grid array. What does it mean? Ball grid array says we have, when we look from the bottom, initially we had the I/Os to the sides. Okay, here it's limited, Then we had IOs to all 4 sides. That was a QFP. And then the idea was by bringing these in an area, and so on, we can have much more IOs on the same area. The trick is the pitch doesn't become much larger. The device becomes smaller and we have more IOs. So that's a ball grid array. A ball grid array cannot be built up on a lead frame, typically. It must be built up on something like a printed wiring board. The first BGA were built up on a ceramic board, but here the disadvantage was that was very expensive, and the CTE of the ceramic is very different from that of a printed wiring board on which it is soldered. So we have much thermal expansion problems. So now let's have a look at the BGA, how it is built up. So we start with something which is a little like a printed wiring board. In fact, it's some kind of printed wiring board. It is called interposer. And that board is already a multi-material board, which can be just purchased in a printed wiring board company. So as a manufacturer, you do not have to deal with such devices. And that board, of course, has a landing place for the chip, and it has some landing places for bonding wires. Okay, so the problem is when we want to glue and when we want to wire bond, typically that cannot be done well on copper, because copper is not chemically stable. So typically the copper is coated, and it's typically coated with gold. Oh, this isn't gold. Why so? The reason is that typically we would have a chemical reaction between the gold and the copper, so some diffusion, and in order to avoid this, we must have a nickel layer in between. So we typically have only layers consisting of, so we typically do not have pure gold layers, but we always typically have nickel gold. typically the gold is, let's say, 0.1, and the nickel is typically 2 to 3 micrometer. The reason is gold is expensive, and the nickel must have a certain minimum thickness in order to avoid diffusion. Okay, so that's something we can buy. It's not so expensive. Maybe costs are only a few cents per square centimeter or so, also depending on how many you get. So the next step is already as we have known it. In fact, you can put printed wiring boards into a molding machine, or you can put in lead frames. So we must again deposit the adhesive. And the adhesive consists of what? For instance, epoxy plus silver, or some aluminum oxide. So it's silver if it should be electrically conductive. It's aluminum oxide if it's only desired it has a certain thermal conductivity. Okay, what is the next? The next is the chip. Of course, in almost all cases, it consists, at least for integrated circuits, it typically consists of silicon. Other materials can also be used, like gallium arsenide and so on, or silicon carbide. And now we must have a look at the surface of the chip. On the surface of the chip, we typically have a metallization. Now my question is, what do we use for metallization of a chip? Can you give me an idea? How is the metallization of a chip accomplished? Give me a proposal. What is a chip metallization? I'm listening. Yes, so okay, yes. I'm positively surprised because in most cases in previous years I got the answer it is gold, but typically you never have gold on semiconductors. You typically have an aluminum alloy. Okay. So to that aluminum, we also have attached a passivation, and in the end we can again do our wire bonds here. Of course, the wire bonds in reality are much thinner. It's only because I cannot paint it so small. And also it must be noted, that's important, that in almost all cases the first bond, which is the ball bond, is accomplished on the chip. So we this avoids damaging of the chip by the bonding compression. Okay. What else do we need? I think we have almost. Sorry?
In the ball, they put on the bit there that they do the ball first, and then you can link up the wires in all directions.
Okay, that's good. But anyway, you could also start on the printed wiring board and then go to the chip. But the reason is the pressure per area is lower with the ball bond, and that helps the chip to survive. But of course, you are right. Ball bonding generally has the advantage. You can, from the bond, you can go away in any direction in a radial fashion, and that makes that bonding process very efficient, and also machinery is easier. So now let's proceed. What we need is, of course, a protection, and we can go here. I don't like it yet. So again, here we do the molding. And there is still one thing which is missing. So here is the molding compound. One thing is missing, and that's the balls. Question is, how can we produce balls? So that's not so beautiful. Also, please, can you repeat? So there are many possibilities for depositing such balls. Maybe I make them a little more beautiful. So that's the balls. The easiest way is to turn this ball grid array and to put a sheet on it, a metal sheet, which is some kind of template, and put it on, and that template has holes. And then we, before we put on that template, we put on a sticky material, like a wax or a resin or so. And then we put on the template with holes, and we take small solder balls which can be produced easily, and into each hole we place one of the solder balls just by pouring a sack of such balls onto that plane here. After we remove this template, only in the places where we had an opening in the template, solder ball will remain sticked to that surface, and then this BGA can just be run through a reflow oven, and then these will remelt and will wet the copper here, and though we have done the balling. We can do it also in other way. We can use a paste and do some screen printing or so. So there are quite a number of possibilities here. So, did I forget something? I don't think so. So we are more or less finished. In the end, we have a laser. What's a laser for? That's for giving the label. In former times, it was printed. Nowadays, we have some constituents which decompose and give this color. Yes. So okay. In that way, we have done a package. Let's say it typically goes from 44 to almost 1,000 IOs. And in that way, that's for high IO numbers. There's another type of package, which is the QFN package. Do you have an idea what that is, QFN? That means quad flat, no lead. That package is not for so high I/O numbers. So typically, it's something maybe in the below 100 or so. That's also depending on the manufacturer. QFN is, for instance, typical for a small microcontroller or such a thing. It's also a SMD device. And why do we have this package? So one of the reasons is we wanted to have a very compact package for, let's say, medium I/O numbers. The second is when the BGA was invented, so that was in favor of the manufacturers of printed wiring boards. But the manufacturers of lead frame, which is mainly Japanese companies, they didn't want their business being spoiled by just a trend in industry. And so they invented a package which is lead frame based. So to that purpose, we start with a lead frame. And here I start with a preliminary sketch. So that's the lead frame. That lead frame is produced by etching. I have to modify it a little. Okay, that's it. So we can etch from both sides, and so we have this semicircular edge profile here. Again, such a metal structure should be coated with some nickel and gold. That was the wrong one. And so here in these locations we have gold. Then we can mount the chip as we have seen it. Also, it's important that package is a so-called chip scale package. So typically, the package size is maybe up to 20% larger than the size of the chip itself. But that's a rough guess. Also, often we have it not that proportion, but in a similar way. So we must add the chip. Again, here we have the metallization. You have the passivation here. Of course, here it is again aluminum. Then we can do the wire bonding. And finally, we mold it. And in that way, we have designed that package, and so that's it. That is our QFN, and that QFN is also a so-called chip scale. Okay. Finally, the copper places for soldering, they are typically coated with a little thin layer of tin. That's for solderability. So if you have a tin surface, it is preserved solderable better than when you have a copper surface. And in that way, today we have seen two modern package types. And okay, also I wanted to tell you today the style of the exercise. So I hope it will work. On the other hand, we will put all of this information on the Ilias, and if you have further questions, the best is you just send me an email. Thanks for your attention.